Hello students, welcome again to the new segment. In this Hello students, welcome again to the new segment. In this segment, we will be looking at how we can create the confusion matrix. Right. So the function that we need to use is the confusion mat, and this function needs two pieces of information. One is the original data labels, and then the predicted data labels. Right. So we need to pass to it these two pieces of information. That is the labels or the class names for the original observations that we are trying to for which we are trying to compute the confusion matrix, and then for those labels, what are the predictions, right? So the predictions can be returned from a certain classification Welcome to Machine Learning course, Supervised Machine Learning Algorithms using MATLAB. So this course essentially contains 12 different segments. So let's see what we have in each and every segment. In the first segment, we will be looking at the instructor and course introduction. In section 2, we will be quickly covering the MATLAB essentials, and those essentials will give you a quick start in order to get familiarized with MATLAB and start implementing your machine learning algorithms. In segment 3, we will be looking at from where we can get the data set and how we can import it into the MATLAB environment. From section 3 onwards, we will be looking at different machine learning algorithms. So in section 4, we will be looking at the first machine learning algorithm, that is k-nearest neighbor. In section 5, we will be looking at another algorithm that is called naive Bayes. In section 6, we will be looking Hello students, welcome again to the new segment. In this segment, we will be looking at another very important name value pair argument for the cross-val function. So we've introduced the cross-val function in the last lecture, and we noted that we need to pass to it the learned model, which we have already created in the last lecture, and then certain name value pair arguments. So now here in this case, the name value pair argument that we want to emphasize is the CV partition. Now this name value pair argument, it needs an object of class CV partition, right? So we need to create that object first, and then we will be able to use this name value pair argument. So let's see how we can create that object of class CV partition, right? So we need to use the function CV partition in order to create an object of type clause validation partition. And then we need to pass to it the number of observation within our data set, right? So we noted that it's 150, but in order it can be of anything. So we can grab that information from our learned model by m.num observation, and it's 150, right? So we can pass this to the CV partition function, right? Num observation. And then the next thing it requires is that you can have multiple options now. Well, you can either say k-fold, right, and then mention the number of folds, or you can say a holdout and then mention how many percentage of objects you want to hold out, for example 0.25 or anything. Or alternatively, you can mention leave out, right? And then with the leave out, since it is understood that it is going to leave one observation for the training, for the testing, and the remaining ones for the training, and it's going to do it the number of observation times, so we do not need to pass any additional information to it. So let's say we do it with a k-fold, with k-fold equals to 5. So when we do that, it's going to create an object of type CV partition, and that object is now C, right? And then we can pass this information into our cross-val function. So with a cross-val function, we need to mention CV partition and then pass to it this object that is C. And then we will learn it into some variable, cross model, right? And then when we press enter, it is going to create that model for us. Now, one thing you may have noticed is that we were we can also specify those pieces of information, like without CV partition, we can mention here k folds, right? And then mention a name 5 for it, and then it will do the same job. So why we are actually considering this CV partition, right? So the answer is that it's actually going to give you some additional information regarding the partition that it has Hello students, welcome again to the new segment. In this segment, we will be looking at how actually good our predictions are. So remember in the last lecture, we have seen the predict and reset predict functions, and the essential job there was to predict the classes corresponding to different instances. Now in this lecture, we will be looking at how much accurate our predictions are, right? So whether we make more correct predictions or incorrect predictions. So we are trying to evaluate that aspect in this lecture. So the first function we need to look at is the loss function. And with the loss function, we are actually trying to look at the predictions in the testing data or the unseen data, right? So we are trying to evaluate the performance of the model based on some unseen data, not the training data. So it requires basically three pieces of information. The first is the model itself, and we built that model in the last lecture. It is a KNN model, and it is based on the RS dataset. And then the second thing we need to pass to it is some data. So let's pass to it some pieces of information. So in this case, we are passing to it one instance, and we know that the RS dataset contains 4 predictor variables. So we need to pass to it 4 pieces of information. And then finally the class. So let's say we are assuming that its color may be RS versicolor. So when we press enter, it is going to give you a value between 0 and 1. 0 will mean all correct classifications, right? And 1 will mean that no classification decision has been correctly made. So no prediction is correct. And in that case, it will have a value of 1, right? So a value of 1 in this case means that this prediction is incorrect, right? So it is an opposite of the accuracy. Similarly, you can pass to it more than one piece of information. For example, we want to pass to it two pieces of information, right? That is 2 instances. Instance number 1 contains this information, and instance number 2 contains this information. And then we need to pass to it the corresponding classes of those instances. And it is saying that it is also not making any correct predictions. So all the 2 predictions are incorrect. Alternatively, you can define a matrix A that contains your data. So let us populate it with some data. So in this case, it contains 4 instances. And then you can create another variable which contains the class names. So let's say RS versicolor. And we need to give 3 class names because we have 3 instances. So we need to make sure that the number of instances, the number of classes should be the same as the number of instances, otherwise it is going to throw an error message. So now we have 2 variables, A, which contains the number of instances, and variable Y, which contains the corresponding classes. So now we can call the loss function and pass to it these 3 pieces of information. One is the model itself, the other one is the data, and the final one is the class names. So when you press enter, it is going to return a loss of 1 again, which means in this case that none of the predictions were being correct. So all of them, if you look at the predictions, you can make sure. So we can use the predict function, pass to it M, and then A, right? And then see the corresponding predictions. So for the first instance, it has predicted RS setosa, whereas the actual class we provided was the RS versicolor. Then for the second class, it is predicting RS virginica, and we have provided it that it is RS setosa. And for the third, RS virginica again, and it is incorrect because we have provided it that the correct class is RS versicolor. The final variant of this function is that you can have large amounts of data, which is normal in this case, right? So generally that is the case, that you have a large amount of unseen data. You want to make predictions for that. So you can read that data into some variable. And remember in the last lecture, we have created that test variable, which contains a lot of data. In this case, it contains approximately 15 instances. And those instances we have seen in the last lecture that if we use the predict function, all of them will be correctly classified. So if you pass to it model M and this testing data T, so all of them have been correctly classified, right? So let us look at what is the loss. So with the loss function, you need to provide to it the model M, the testing data, and when you pass to it the table data structure which contains the testing data or the unseen data, then you need to Hello students, welcome again to the new segment. In this segment, we will be looking at the error correcting output code in symbol-based classification. So the first function that we need to use is the fitCECOC, and we need to give to it two pieces of information. One is the data set itself, and I have already read the data into the variable X. It contains the RS data set, and we need to return it into some variable. So let's say M. And then after it will learn the corresponding error correcting output code model. So now let's directly go into some very important name value pair arguments that you can set for this classification method. So the first one is decoding. Right, so some of the available options that you may try here is the all pairs. So this argument actually controls how actually the codes are being assigned to different classes. So all pairs is the first option. Then you can try binary complete. And similarly, you can try another one that is one versus all, and then ordinal. Or you may be interested in some random ones, or dense random will randomly assign those codes to individual classes. So now let's look at the differences between these different schemes, because they are very much critical to the underlying performance of this ensemble-based classification method. So let's see that. I have created this document, and I will share it with you after I explain all of them to you. So the first one is all pairs. And alternatively, the second name of this very same approach is 1 versus 1. So here, the essential approach in assigning different codes to different classes is that it will consider each pair of two distinct classes, and it will consider one class as positive and another one as negative. And it will consider all the class combinations that are possible. So if we have a 3-class problem, so now all combinations will be 3, because class 1 versus class 2, then class 1 versus class 3, and then class 2 versus class 3. So all combinations are 3. And then in the first combination, it is going to learn a binary model that will discriminate class 1 from class 2, and it will ignore the instances from class 3. Then in the second binary learner case, it will learn how it can discriminate between class 1 from class 3 and ignore all the instances from class 2. And then similarly for the third combination, it is going to consider a binary classifier which will discriminate between class 2 and class 3. So the codes here are assigned based on all the combinations, and it will consider 2 classes at a time and ignore the third one, right? The second one is the binary complete. So in this case, there are 2 requirements that it needs to set. First one is that it will assign to each individual class, it will assign codes that have at least one positive and one negative value, right? So here all the values are, I put zeros because for the binary, in order to explain the binary nature. However, you can consider this 0 as -1 and the 1 as +1, right? So this will not be considered, right? Because it contains all of them is having the same value, that is -1. That is the first constraint. And please note that in binary combinations, when we have a certain number of variables, let's say n variables, and we want to draw all the combinations, so in general there are 2 raised to the power n combinations corresponding to n variables, where each and every variable n can contain 2 possibilities, either 1 or 0. So since we have 3 classes in this case, so we have 8 possible combinations for all the 3 variables, right? For all the 3 classes. So according to the first constraint, this is not going to be considered, because for a particular class, the restriction is that there should be at least 1 plus and 1 minus sign corresponding to that class. So this will also be not considered, because all of them are having the same class labels. Now, the second restriction is that if we are considering 2 codes to be valid codes, then at least they should differ by 2 values, right? So here, if we consider this code as a valid code, so if this is valid, I will make it green, then this code will be valid if it differs from this code in at least 2 positions, and it did, so we will also consider this as a valid code. Now, this is not a valid code because from this particular code, it only differs in only 1 value. These 2 values are same, these 2 values are same, but it only differs in 1 value. So this is not going to be considered. Similarly, this one will be considered because it differs from this in 2 values and also from this in 2 values. And these 2 will not be considered because of the very same reason, because they do not differ from any of these codes. From some of these codes, they only differ by 1 value. For example, from this code only differs in 1 value, so this will not be considered, and also this will not be considered. So we have 3 possibilities left. So in general, if you want to have the mathematical definition of it, so in general it will generate 2 raised to the power k minus 1 combinations. So if we have a value of 3, so 2 raised to power 3 minus 1 is 2 raised to power 2, which is 4, and 4 minus 1 is 3, so it will consider 3 combinations for the codes. This is binary complete. The other option is 1 versus all. In this option, for each binary learner, 1 class is considered as positive and the rest are considered as negative. So if we consider the rows corresponding to different classes, so class 1 is considered positive, and then the rest of the 2 classes are considered negative. Similarly, again, Class 2 is positive now, and the rest of the two classes are negative. And finally, class 3 is positive, and the rest of the two classes are negative. In this case, it will also consider k number of instances, k number of codes, where k belongs to the number of classes. So if we have 4 classes, we will have another column over here with the values -1, -1, -1, and +1. Right? Finally, we have the ordinal method, and this ordinal method is a little bit different from the one versus all method, and it will generate k minus 1 binary learners, and the learners are created in such a way that in the first learner, the first class is negative and the rest of them are being positive. So this one will be considered as negative, the first class, and the rest two are considered as positive. Then in the next case, class 1 and class 2 will be considered as negative, and then the third one will be positive. We do not have a third row here because it is not allowed to have all the classes as having belonging to the negative category. So if we push -1, and then -1, so it is not allowed because this binary learner is not going to learn anything, right? So it will not discriminate anything from any other thing. So these were some of the options that you can try. And of course, here with these 1-0 combinations, you can always replace this 0 with a -1 in order to make more sense out of the corresponding example, right? And so on. So this was a few notes regarding the coding property. And of course, you can also generate the codes to be random. And the option that you can use for that is the sparse random or dense random. Again, the two approaches changes in how the randomization is being applied. Right? So in that case, the codes will be assigned at random. So in the next few lectures, we will be looking at some more name-value pair arguments. So stay tuned. In this segment, we will be looking at how we can compute the ROC curve and the area under the curve and the statistics such as the true positive rate, false positive rate, true negative, and so on, right? So let's directly start. So the function we need to use is the performance curve. And this function actually needs 3 pieces of information. So the first thing you need to supply to this function is the class labels. That is the true class labels, and then you need to pass to it the classification scores corresponding to different instances, right? And you need to specify for a particular class, right? So for each and every class, this function needs to be executed. So we know that for an ROC curve, in order to generate that, we need to have at least one positive class and one negative class. So we need to specify the scores corresponding to the positive class. Right? So we will look at an example, and it will In this segment, we will be looking at the intuition behind error correcting output codes classification. So the first thing we need to note is that this method is being used to deal with multi-class classification. That is the classification that involves more than 2 classes. So the classes can be 3, 4, 5, up to so on. The next thing it's going to consider is that it is going to assign binary codes corresponding to each and every class. Remember that the binary codes needs to be unique for each and every class. That is, we cannot assign 2 classes the same binary code. So by binary code, we mean the code containing 1s and 0s only. So the length of the code can be of different, but for all these classes, there has to be the same length. So in this case, we assign codes that has a length of 3, right? And remember that these codes can be assigned in so many different ways, and we are going to cover some of those when we cover the implementation in MATLAB, right? So we will cover that there. For now, just consider that we considered some approach, and based on that approach, we are able to define these codes for individual classes. Now the next step is that we are, depending on the length of the code, we are going to define that many binary learners. By binary learners, we mean that we are going to use some classification algorithms such as the Canon, the naive Bayes, the SVM, and so on. And they are going to be implemented based on a binary classification problem corresponding to each and every bit of code, right? So we are going to consider the first bit in all of these codes corresponding to different classes. And then this code will be used in order to learn classifier 1. And the classifier 1 is going to learn it in such a way that it is going to consider the class 1 and class 2 as negative class and class 3 as positive class, right? So it will consider these two as one class that is negative and this one as positive. The classifier learner 2, which is going to consider class 1 as positive and then class 2 and 3 as negative. And then the learner 3, it is going to consider class 1 and 3 as negative while class 2 as positive. So now the next step is that how we are going to classify a new instance. So a new instance has arrived, and then we are going to pass this new instance to all the 3 learners. So for instance, learner 1 predicted its class as positive, learner 2 predicted its class as negative, and learner 3 predicted its class as negative as well. So then the next step is to consider its differences with the codes that we assigned earlier to individual classes. So if we look at the differences, right? So it is the same, it is the same, it is the same. So there is no difference between this instance and class 3 code. So we can say that the distance between this class and this new instance is 0. That is, they are exactly the same. If we compare it with this code of the second class, so we may note that there is a difference. So 1 difference and 2 differences. So we can say that the distance here in this case is 2, right? Similarly, for this class, there is 1 difference, there is another difference, so 2 differences. So we are going to classify this new instance to the class that has the minimum distance or the greatest similarity. So it has the greatest similarity with class 3, so that's why this new instance is going to be classified as belonging to class 3. Right? So there are a few more research issues. That is, if you make these learners more, that is, if you increase the code length, then it's probably going to increase the classifier performance. And then we should not assign 2 codes that are similar, right? So we cannot assign 2 classes the same code. Then the distance between the codes, that is, the individual differences within the codes should have follow some minimum criteria. That is, if we note here that the differences between this code and this code is 2, while the difference between this code and this code is also 2. And if we look at this, so this has also a difference of 2. So we noted that all the codes differ by at least length of 2, right? So we want to maximize this distance as well. So this distance also plays a very critical role when you try to learn these individual models and make predictions. So that was a very simple approach, and sometimes it is also considered as an ensemble because it is based on classification of multiple individual classifiers, and it is going to integrate all those classification decisions and make a single classification model out of that. So that's it for now. Hope you're enjoying the course. See you in the next segment. Hello students, welcome again to the new segment. In this segment, we will be looking at the intuition behind support vector machines. So let's start. So the essential idea behind support vector machines is to find a hyperplane that will separate the data of the two classes. So in general, it works with two classes, but there are extensions which extend it to multiple classes. So when we have the data of the two classes, so let us suppose these circles represents class 1 data and these square boxes that represents the class 2 data. So it will try to find out a hyperplane that will separate the instances from the two classes. So one possible solution can be this hyperplane. Right? So this is a linear separator which serves as a decision boundary between the two classes. So for instance, if a new instance arrive and it is on this side of the hyperplane, so we will be classifying it as circles, and if it is on this side, we will be classifying it as squares. So that's one possible solution of a hyperplane. But if we observe and have a close look at this example, so we may note that there are other hyperplanes as well, right? So for instance, another possible solution can be this one. Or alternatively, if we put a more closer look, we may observe that there are many other hyperplanes as well. So now, which one of these hyperplanes the SVM is going to consider? Well, the question now reduces to that which of the available hyperplanes are the better ones. So for instance, if we have two hyperplanes, so is B1 better or B2 is better? So the SVM philosophy is to consider the margins. So remember, the margin is actually the projection of the individual instances onto the hyperplane, the perpendicular projections. And then it is going to consider the projection of the nearest positive point or one class data and the nearest the other class data, and then it will call this distance as the margin, right? So here the margin for this hyperplane is starting from here to here, right? Similarly, for this hyperplane, the margin is a little bit lesser because the projection here is this much distance, right? And here we have this much distance. So it actually sometimes it calls it a street, wide street, right? So here the width of the street is very narrow. Here the width of the street is quite large. So this hyperplane is going to be better compared to this hyperplane. Please note that the instances which are closest to the hyperplane, in this case, which are being used to calculate the margins, they are referred to as support vectors. So if we consider this hyperplane, then this and this is going to be the support vectors. If we consider this as our hyperplane, then this instance and this instance are going to be the support vectors. So the other restrictions on support vectors is that you should have at least one support vector from each class, right? So that's how the SVM works. Now, it may not be always possible to find out a hyperplane which exactly separates the data corresponding to the two classes from each other. So for instance, if we look at this example, so this, if we consider this hyperplane, so then this point is going to be misclassified and these 2 points are also going to be misclassified, right? We will classify it as belonging to the square class. If we consider some other hyperplanes, so we may not be able to find out the exact boundary. So for instance, if we consider this one, so we are still able to there are still a lot of misclassifications, such as this one will be misclassified and this one will also be misclassified. So in these cases, we call these cases as linearly not separable cases. That is, we are not able to find out a hyperplane which exactly separates the data of the 2 points from each other. So what are the possible solutions in such a case? Well, essentially, there are many solutions, but the 2 of the most common ones are, number 1 is to still classify with a hyperplane, but by allowing for some misclassification. That is, we will have a hyperplane with some constraints on the misclassification rate. And again, the hyperplane which leads to less misclassifications will be preferred over the hyperplane which leads to a lot of misclassifications. Another approach is to map to a higher dimensions, and then when we map to a higher dimensions, we may be able to find out a hyperplane there which can separate the data from the data of the 2 classes from each other. And then there is a notion called kernel trick, which is used when we try to implement the second strategy. So let us look at the second strategy, and suppose we have a 1D data. So these red points corresponds to one class data, and these black points are the data from the second point. So in this case, if we draw a plane over here, a hyperplane, so it is going to misclassify those 2 instances, right? So we may not be able to exactly classify that. If we put a hyperplane over here, so then there will be some misclassifications as well, because these 3 points will be misclassified. Right? And if we put it over here, then there are a lot of misclassifications. So we are not able to linearly separate these these set of data points. So if we map it to a higher dimensional space, what do we mean by higher dimensional space is, let's say, a 2D space, and then find out a function there, and then we will try to project these points onto that function, and then we will try to see whether we can separate that or not. So if we consider the equation of parabola in 2D, and then map these 1D points onto that parabola, then we may note that we have a very good linear separator which can separate the data points quite easily without any misclassifications. So now there are a lot of research questions, such as whether it is always possible to do that, is the functions always exist, right? And furthermore, there are a lot of computational overhead, so how to reduce that computation overhead? Well, when we move from simple dimensions or lower dimensions to higher dimensions, the computations are going to exceed, right? So these are some of the research questions. In order to deal with the second research question, there is computational aspect. So there is another trick that is frequently called the kernel trick, which actually try to avoid those computational aspects that are involved with the higher dimensional data. So I think that's enough for the SVM. Hope you're enjoying the course. See you in the next segment. Hello students, welcome again to the new segment. In these segments and some of the upcoming segments, we will be looking at how we can actually evaluate the performance of a classification model and those classification models that we have been developing so far within this course. So the first thing we should note is that in order to evaluate the performance of a classification models, there can be different aspects to this. Right? So the first aspect can be that we are trying to evaluate the performance of a classification model based on the training data itself. That is, we want to look at how well the model fits the training data itself. The second aspect can be that we want to evaluate the performance based on some unseen data, right? The data that is not part of the training, right? So we have not used the data for the training purposes. And a third aspect can be that we want to evaluate the performance of different classifiers, right? So we want to make some comparisons between these different kind of classification algorithms. So the MATLAB actually provides you with different types of functions in order to carry out each of these individual aspects. So let us look at some of the functions. So remember that the first thing that we may want to do is to make some predictions with the classification models that we have developed. So the first function we look at is the predict function. With this predict function, you need to pass to it certain classification model. I have already made a classification model M, which is a Canon classification model, and I will pass it to this particular function. The second argument this function needs is some data. Right? So since this model M was being built with the RS dataset, so in the RS dataset we know that there are 4 predictor variables. So we need to pass to it 4 pieces of information, which makes up one record. So when you press enter, it is going to return the predicted class based on this model M. So if we have more than one instance, and those are being saved in certain metrics. So let's say we have 3 instances in this case. Right? So we can pass those to the predict function with the model M, and then it will give us predictions corresponding to each and every instance that belongs to the matrix A. Right? So in this case, it is saying that the first instance, the predicted class for the first instance is the RS setosa. For the second instance, it's RS virginica, and similarly for the third, it is also RS virginica. So that's how we can actually pass to it more than one instance. Alternatively, if you are having a large data set and large pieces of data set that are unseen data, and you want to predict its class, so you can read that into a certain table and then pass that table to it. So let's do a quick example on that as well. So remember, we have been working with the RS setosa dataset, and that is stored in 1.csv file. So that's the file, right? So let's have some instances from here. Let's say 5 of them. And we will make another file, that is the test.csv, which is the unseen data. And we are going to paste it over here, right? Similarly, some more instances from the second class, which is this one. And then for the third class, we will also paste some instances over here. The third class Hello students, welcome again to the course. So in this lecture we will be looking at the basic graphical user interface of the MATLAB. So let's go directly and start. So the first thing you may encounter is this command window. This is the window which is spanning majority of the screen, and this is the place which we will be using more frequently within the entire course, and it is the place where we actually interact with the MATLAB software. What do we mean by that is that we are going to give certain inputs to the MATLAB software and then expect some processing that is done on our behalf by the MATLAB, and then we expect certain outputs, and that will become visible here on this command window. So we will be using it very frequently. For now, you may give it some meaningful calculations, right? So here you may think of it as a very big calculator, but of course it is beyond that, right? So it can do more operations than the simply calculator can perform. Okay, so some of the other windows that you may look at here is the workspace. So it is going to hold the results of our computations. That is, if we assign our computation to some variables, so it is going to hold that variables for us. Then there is another window that is called the current window. It is basically a dedicated folder which will store our scripts and programs that we want to run and we have saved using the MATLAB software. You can change this default dedicated folder, and you can do it from here, right? Remember that you cannot go up in the directory levels from here within this window. You can just browse within a certain directory that is specified by here. So in the MATLAB directory, there are these, this is the directory structure, right? We can further explore that. But you cannot go up in the directory. If you want to go up, you need to use this this small area, right? So you can go up and select an appropriate place where you want to store, or if you want to change your default directory. Then there are some tabs at the top. This is the home tab, where you may see some of the conventional options, such as you want to open certain script, right? So you can mention that, or if you want to work with a new script and so on. We will be covering some of them later on in the course, and they will become relevant as we progress along the course. For now, you can just familiarize yourself. This is the plotting option. So there are different plots available for plotting your data and visualizing them. Of course, there is another one which is called apes. So you may consider it just like an app store, which contains a lot of different apes. And only the apps that comes with the MATLAB distribution are going to appear over here. You can add and delete apps from here, right? And these apps corresponds to different fields such as math, statistics, control system, signal processing, image processing, and so on, right? So these are some of the popular apps from databases, from computational biology, and so on. For now, let us consider some more meaningful operations. So let's say we want to define certain variables. So all the operations we did so far, they were not being stored with us, right? So let us try to store them. So you can assign it to certain variables like this with an equality sign, and then it will be stored in this variable A. So when you press enter, you may note a sudden update here in the workspace, right? A equals to 8. So you can do some more operations. For instance, you can say B equals to variable A minus 4. Now the variable A value is going to be put over here, and then 4 will be subtracted from that. So you will notice another variable over here. So that's how this workspace is going to be updated. And you may also note that there is a default variable called ANS, right? So if something is not being stored into a variable and MATLAB performs some operation over here, so then it needs to store that, right? And if you don't mention any variable, it is going to be stored in the default variable, which is ANS, right? So if we do something like this, right? So now you notice that ANS has been assigned this value, right? So that's the default variable if you don't mention any variable name. So in the next few lectures, we will be looking at some more details, so stay tuned. Hello students, my name is Dr. Noman Azam. I received my PhD from University of Regina. It is in Canada. I had over a decade of experience in research and teaching at the undergraduate and graduate levels. On the online learning platforms, I teach MATLAB related courses on different online platforms such as the Udemy, the Skillshare, the Skillwise, Stake Commerce, Stake Skills, and many others. On the Udemy, you will notice my courses, they are listed on the very first page in the MATLAB niche. And so this is my course. This is the best-selling course. Similarly, this is another course, and this is also my course. With regards to research, I have investigated the use of machine learning algorithms in different applications, such as text summarization, protein function classification, which is a subdomain of bioinformatics, topic modeling, which is a subdomain of text mining, similarly recommender systems, malware analysis, which is a subdomain of security, medical decision making, similarly spam email filtering, and many others. I'm really looking forward to see you in the course. So see you in the course. Hello students. Welcome again to the new segment. In this segment, we will be looking at some more properties of the decision tree classification model. So remember, in the last lecture, we built two models. One is the MCATE, which is the model for categorical data, and the MNUM, which was the model that we created for the numerical data. So let's view the numerical data model, that is the decision tree corresponding to the numerical data. So we need to set the mode to graph, and then it will generate the corresponding classification tree. So we will be frequently referring to it. So that's why I just created it at the beginning. So the first property that we want to look at is the isBranch node. This is going to return a logical array. By logical, we mean that it can hold either a value of 1 or 0. 1 means true and 0 means false, right? Or yes or no in this case. So in this case, this is telling us that whether a particular node is a branch node or it is a leaf node. So we look at that the node number 1, it has a value of 1, so it means it is a branch node. The node number 2, it is not. Node 3 and 4 are the branch nodes, and node 6 is the branch node. So we may look at the corresponding decision tree, and we may note that yes, the node number 1, it is a branch node. Node number 2, it is not a branch node, which means it is a leaf node. Node number 3 and node number 4, they are the branch nodes, right? Branch, and so on. So that's quite useful if you build a complex tree and you want to keep track of the leaf nodes and the branch nodes. The other property that we want to look at is the node class. So in this case, it is going to return a cell array, and it is going to return the most probable class at each node. Right? So if you look at the node number 1, it has the most probable class is Iris setosa. Similarly, for node number 9, the most probable class is Iris virginica. Right? So this is node number 9, and the corresponding class is Iris virginica, which in this case is the same. So a question might arise that how it actually computes these values for the branch nodes, right? Here we do not have the corresponding class label, so how it is going to compute that? So one way of answering this question is that if we prune it, we get the corresponding class, that is Iris versicolor, right? And this is the corresponding class of that node 6, which is being written over here as well. So node number 6 is this one, Iris versicolor, and here we have, if you prune it, we get the same class. In simple terms, it is just the majority class for each and every node that we may encounter within this particular tree. Right? So if you prune it all the way to node number 1, it is going to be Iris setosa, and this is Iris setosa. Right? So in this case, it is giving it just a random value because all the classes here are equally probable. That is 50, 50, and 50 instances for all the classes. If you want to look at here, so 50, 50, 50. So in this case, I believe it has just picked this out based on some randomness, or either because it has the lowest index. So that's maybe the point. But in general, it is going to pick up the most probable class for each and every node. The other property that we may look at is the node error. This is going to tell us the classification errors that we may encounter when we make decisions at a particular node. So remember that if we want to classify at node 1, so the corresponding classification error is 0.667, and that's because if we generate the tree again, that's because if we prune it all the way here, right? So the corresponding class is RS setosa, but in this case we may note that all the classes has the same instances, right? 50, 50, and 50. So it means that if we say that each and everything is RS setosa at this particular node, so we may be misclassifying 100 out of 150 instances. So if we take the misclassification error, it is going to be 100 out of 150, which is exactly 0.667. So if we look at node number 2, there is no error. At node number 2, we have 50 instances, and all those 50 instances belongs to the very same class, right? So 50 over 50 is 1. So misclassification in this case is 0. Similarly, if you look at node number, this is node number 3, so we are misclassifying, if we are saying that everything is versicolor, so we are misclassifying half of the instances, which means its error probability is 0.5. 50% of the objects will be misclassified. So similarly for the other nodes as well, this node again will have a error probability of 0, because all of them belongs to the same class. 47 out of 47 belongs to the same class, so this has an error probability of 0. Misclassification error probability. The other important property is the node probability, right? So it is actually the number of instances from data that satisfy the condition for that particular node. So if you look at this node, every instance in the data set will have this condition. Either it will be less than or greater than or equal to 2.45. But however, if you look at this node, so this node is a combination of this condition plus this condition, right? So only 100 objects will be included here that satisfy this condition. That is, they are greater than 2.45 and then less than 1.75 and greater than 1.75. Similarly, at this node, we may have more reduced number of instances, and that are only 48. So that's actually representing the probability for at a particular node, that how many instances is going to satisfy that condition. So here only 48 objects satisfy the conditions which are prior to that. So if we look at 48 over 150, let's give us the corresponding probability. In this case, it is performing some rounding off, so it is closer to that, right? So another important property is the node risk. So the node risk is actually the Gini index value at a particular node weighted by the node probability. Right? So for Gini index calculation, we need to consult the corresponding theory, but it is in general, it is the Gini index value at a particular node. So there are 9 nodes, so this is the Gini index value at node number 1. This is the Gini index value of node number 2, and so on. Remember that these Gini index values are weighted by the node probability. Some more properties. The size property. The size property tells you how many objects are going to are being included at a particular node. So if you look at here, this contains all the 150 instances. This contains 50 instances, so right? So node number 2, 50 instances. This is node 2, 50 instances. This is node 3. It has 100 instances, and so on. The next property is the number of nodes. So we say num nodes. and it is going to give you the total number of nodes within the tree. Yet another property is the parent property. The parent property is going to tell you the parent of a particular node. So for node number 2 and node number 3, its corresponding parent is node number 1. Similarly, for node number 9, its parent is 6. For node number 8, its parent is 6. For 7, 4. For 6, it is also 4, and so on. Remember that this 0 means that the parent of the root node is always 0, so there does not exist any parent for the root node. So that's why it's get a default value of 0. So these were a few of the more important properties. Hope you're enjoying the course. See you in the next segment. In this segment, we will be looking at some more key information regarding the MATLAB and how the MATLAB is going to work. So in the last lecture, we have highlighted the use of variables. So for instance, we have declared some variables that is called a equals to 8 or a equals to 9 and b equals to 10 and so on, right? So the first thing you note is that if you press the up arrow key, it is going to give you the result of all the commands that you have executed on the MATLAB command window, right? And it is also going to give you a timestamp for that. Right? So if you close the MATLAB and restart the MATLAB, then there will be a new timestamp that will be added alongside with those commands. So if you come later on tomorrow and open the MATLAB again, so there will be a new timestamp. Or if you close the MATLAB and then reopens it, then again there will be a new timestamp. So it will tell you at which time you executed which of the commands. Right? So it's quite helpful in order to keep track of all the commands that you have executed on the MATLAB software. The next important command that you should note is the whos. When you press enter, it is going to give you the information regarding all the variables that are currently being stored in the workspace, right? And some few statistics about that. For example, its size. Remember that each and every variable in MATLAB is going to be treated as a matrix. So if it is a single variable such as a equals to 9, then in that case it is a 1 cross 1 matrix, right? So this one stands for the rows and the second value stands for the columns. So 1 cross 1 means 1 row cross 1 column. We will be looking soon how we can define matrices of bigger sizes, right? But for now, you should note that each and every variable in MATLAB is treated as a MATLAB, and that from where it name comes from, that is the matrix laboratory. So the next thing you may note is that CLC command. So when you press this command, it is going to clear your screen and you will see nothing on your screen. So completely blank screen, right? Similarly, if you want to delete some of the variables from your workspace, so then you need to use the command clear and then variable name. So it will clear that variable from here, right? So we do not see any variable here with the name A now, right? And if you look at whos, so the A is not going to appear over here now, right? So it has been deleted from the workspace. Similarly, if you want to change the name of the variable, you can do it from here, right? You can edit its value. And moreover, if you want to save certain variable, so you can save it onto the memory, right? And it will be saved with the name .net, right? So let's save it here in the default directory. So then we will call it, let's say, give it some meaningful name. So let's say I give it a name, my variable. Right? So now it has been stored in the MATLAB directory, and we can have a look at it here, right? That is the variable that I just saved. So if you want to load this variable, you just need to double click it and it will load it into the memory again. Please note that when we double click it, so then it is going to load under the same variable name on which we have saved that, right? So we saved it with the variable name b, and then we change the name over here, but this name actually does not have any effect when we load it again, and it is going to be loaded within the same variable. So if you want to make sure that yes, it has been loaded correctly, you can clear all the variables and then double click it, and then you may note that it is going to be loaded under the same variable name that we have used it in order to save, right? So that's how it's going to work. So now let's look at some of the matrices and how we can define matrices within the MATLAB. So in order to define matrices, you need to use these square brackets, and then within the square brackets you can mention some values. So whenever we press a semicolon, so then it's expecting the second row of that matrix, and individual values within a matrix are going to be separated by a space. So now it will create a 3 cross 3 matrix. Please note that within the matrix, the number of columns must be the same, right? So the rows has not any restrictions, but the number of columns in each row, they must be the same. So if we define a matrix like this, it is going to throw an error message because the number of columns within this row are not matching the number of columns over here, right? So it is not allowed. So the number of columns must be the same. Now once we define this matrix, you can have access to a lot of different functions, and the first thing that you may note here is that the A has now been updated and it has all the metrics corresponding to it. So if you double click it, it will show you all the values corresponding to that matrix, right, in this form. Similarly, you can add more statistics over here. You can add the range, the mean, median, right? Similarly, the max, the standard deviation, the min, max, variance, standard deviation, and so on. And you can view that with those statistics for this particular matrix by scrolling down here. So it will show you the size, the variance across its different values, the minimum value within this matrix, which is 5. Similarly, the maximum value, that is 9, the standard deviation, the median, and so on. So please also note that since this was a 1 cross 1 matrix, its min max will be the same value because it contains only one value. So 10 is the minimum as well as maximum. There is no standard deviation, and the median is 10 as well. So these values are not very much meaningful when you have a 1 cross 1 matrix. Rather, they become more meaningful when you have bigger sizes of the matrix. Now let's look at some more functions that you can perform on top of the matrix. So remember that we have access to the variance, the minimum, maximum, standard deviation, and so on. So suppose we have this matrix A, which we just defined. So if we want to have access to the minimums across the columns, right? So for that, you can use the function min A, right? And that will give you the minimum across different columns. So remember that this is the minimum of the entire matrix. And with this function, you can get the minimum across different columns. Similarly, if you want to have a look at the minimums across different rows, so in that case, you need to pass to this function minimum 3 arguments. One is the matrix for which you want to perform the row-wise minimums. And then you need to pass to it this empty matrix. This is the syntax of MATLAB. And then you need to say 2 over here. And then it will give you the minimums across the rows. So remember that this min A, this is essentially equivalent to min A, and when you mention 1 over here. So these two sentences are equivalent. When you press enter, it will give you the same result as this one. An alternate way of finding this minimum across the rows is to just take a transpose of the matrix A. So when we mention any matrix name and then followed by a single quote, it is going to take a transpose of that matrix. So you can verify that. Right? So now this A, this is the transpose of this matrix A, right? So 5, 8, 7, they become the first row over here. And then you can call the function min with the transpose of that, and then it will perform the row-wise, but it will show you the result in columns, right? So the result is not row-wise, but the result is row-wise, but actually you have visualization of that it is a columns min. Similarly, there is another function which is called the max. It will give you the column-wise maximum, right? And if you want to have a row-wise maximum, then you can use either the transpose or just use this syntax, right? Okay, the next thing is the mean. So if you want to have a mean across different columns, you can mention that. And if you mention 2 over here, then it is going to give you the mean across the rows. And another way to get the mean across the rows is to take the transpose of that. It will have the same value, but it will just change the display style, right? So that's how it's going to work. If you want to get the mean of the entire matrix, so then you need to mention it twice. You need to first calculate the mean across the different columns and then take the mean of that, and then it will give you the global mean of all the matrix, which is 7.78 in this case. Similarly, if you want to have a minimum across the entire matrix, so then you need to use it twice, min a. It will give you the minimum of the entire table. Similarly, if you want to have a max of the entire matrix, you need to use it twice, max of a. It will give you the maximum value across all the entire matrix A. Similarly, there are other functions. There is the sort function, right? It is used for sorting the values of the matrix. So when you say sort A, it is going to sort these values. But remember that by default, it is going to sort across the columns, right? So these are in sorted order. If you look at A's, right? So this column was not sorted, but it has now sorted that column. So this column was also not sorted. If you want to sort them based on the rows, right? So you can mention that by adding an additional argument over here. Similarly, if you want to sort them based on not in ascending order, but rather in descending order, right? That is, the greatest value should appear over here. So then you can mention an additional argument over here, that is descent. Descend, right? So it is going to sort them now in descending order, right? Similarly, if you want to do it on the rows, right? So you can take transpose and then mention it over here, and it will do the job for you. An alternate way of sorting based on the rows is to just mention sort A and then mention the dimension across which you want to sort. So it will sort now based on the rows, right? But again, by default, it is going to do it in ascending order. If you want to mention it in descending order, so then you can mention that descend. And it will now sort by rows, but in descending order, right? So the greatest value is here and the least value is here across all the rows. So these were some of the common operations that you can perform on top of the matrix. Of course, there are a lot more details, but we only concentrate on those details which are relevant to this particular course. So hope you're enjoying the course. See you in the next segment.